So it's quite related to sort of landscape decision workshop, but I tend to be working in something that's more forecasting based, where there will be policy decisions made on the sorts of analyses, or hopefully the sorts of analyses that we're doing, but there aren't so much policy levers to be pulling. But how you communicate the uncertainty and the forecast, particularly when you're dealing with rare events, I think is you know, really interesting and sort of wide open thing. Oh, so this is there's some very old work in here, and some of the newer stuff is particularly with colleagues in Edinburgh and at the Volcano Disaster Assistance Program, which is joint U.S. State Department and the USGS, and my colleague at Duke. It's also nice to be here because it enabled a couple trips to Edinburgh while I'm here, which is nice. So volcanic hazards in particular, which is going to be the focus of this talk, although I think we're sort of starting to think about other similar geospatial hazards, really started with Mount Pelée in Martinique. And one of the issues that both, I think, sort of society feels and geologists feel is that volcanoes behave as they will in the past, as they have in the past, right? So there was still some cultural memory. Is there a, that guy, the pointer? Yeah. There was still some cultural memory about 50 years before the volcano turned on in 1902. And so when there were signs of unrest, people were like, oh, it's going to, you know, before there was some degassing and some small events, but nothing major. But instead, they were sort of had a massive pyroclastic density current, which is sort of the opposite of Hawaii, right? So, so there's lots of news about Hawaii, and it was sort of super fun for volcanologists I knew to be experiencing that real time. But the threats there are very slow and they're very localized. Here, these threats are rapid, these sort of massive volcanic landslides effectively, where the edifice is breaking up and expanding and going tens of kilometers per hour is something you can't outrun, and here killed 30,000 people. Other volcanic threats come from ash, and there's sort of two threats from ash. There's this large-scale affecting aviation threat, which you guys here are pretty familiar with. There's also, more locally, tephra fallout or tephra deposits. And those can, and it's a funny thing. In some ways, these hazards feel binary. I was talking to Marcel about this yesterday, but they're not always, right? So you're interested in some, am I not affected? Am I affected a little bit, or am I completely toast, right? And for tephra fallout, this can happen quite locally, and a little bit on your roof will be fine. A lot of tephra falling on your roof will collapse it, right? So, so you're interested in not quite a binary, but an on-off system that could get worse. Here's another kind of volcanic hazard, which is a lahar. So in some ways, this is a coupled hazard with a pyroclastic density current. You have to have deposits from a pyroclastic density current, which are basically ash and boulders, and then some big rain event or glacial melt that remobilizes this material. Then you have this sort of two-phase material that has this nasty feature. I don't know if any of you had a physics class about granular materials, but there's this sort of analogy that if you have a can of mixed nuts, all of the big nuts float to the top. If you have a lahar, all of the boulders float to the front. Right, so you have this sort of massive mudslide that is sort of trudging along with boulders at the front. Right, so and these things are quite dangerous. And then the kind of thing we might be interested in is, okay, well, A, there has to be somewhere where there's PDC deposits, so you have to be thinking about that. But then what about, you know, in the changing climate with rainfall intensity and duration changing, how would that affect regions that are prone to lahars? We've been applying just recently similar approaches thinking about storm surge. So this is some storm surge from Hurricane Michael last fall. And storm surge is when, so the hurricane sort of headed up this way. This was a forecast of the surge levels. And it's basically the wind of the storm pushing water onto the land. So again, we have this sort of binary, not quite, binary plus a scale of badness, right? So in South Florida, now if you're building a new house, it has to, and you're very near the coast, you have to be raised so much. I don't remember the numbers, but maybe half a meter or a meter. So perhaps you're okay with a storm surge that is half a meter tall, but 5 meters would be terrible. Right, so these are the sorts of things we're interested in. And again, if we're thinking about sort of potential future scenarios and how these storms might be worse, we'd like to be able to explore sort of given current distributions of storm characteristics versus potential future versions of storm characteristics, how might that impact these regions? And that might, again, be helping set some policy for who can build where and what levels would we need to be building at. Okay, so back to volcanoes. So this is Montserrat, which is kind of this, the best studied volcano ever, I would say, mostly because of the BGS. And you can see some pyroclastic density currents. It also is subject to lahars and tephra fallout, but mostly here I'm going to talk about these PDCs. And there's still, sometimes you'd like to put problems away and move on, but there's still interest in this. So here's the record of PDCs in the last, 20-some years at Montserrat. And we see this sort of periods of high frequency and lower frequency cycling. And the last PDC event was in 2013. So this question is it over? Right? So that's a good question. And so I've been charged with sort of presenting some of this work I'll go through to the Scientific Advisory Council at Montserrat, because this is the current sort of evacuated zone here. A lot of money for the island is going to come from mining the volcanic material. So what they'd like to do, since perhaps it looks like it's over, is they would like to set up ports down here, and they would like to bring in mining equipment and potentially have some camps down there, right? And so when should they do this? Should they wait much longer to see if this is a good plan, right? This is the kind of thing they're wanting to make decisions about now. Okay, so is it over? So this is a sort of world record of volcanoes. So we have duration on the bottom and a log scale of sort of an eruptive period. And we have the number lasting, sort of frequency, the number lasting more than T years going up. And this guy is pretty close to linear. And basically what it's saying is if the volcano's been going on for a long time, there's a good probability that it's going to last even longer. So my colleagues had modeled this this volcano duration as a generalized Pareto distribution with some uncertain parameters. And we can think about this then in forecast mode, right? So here, if we know it's already been active for tau years, and you're interested in what's the probability it's active for another t years, that also follows this generalized Pareto distribution. So now I can say, okay, how long would I expect this to remain active for? This is for a whole series of volcanoes. Montserrat is the one that's highlighted there. And so there's a good chance it'd be active for another 50 years, right? Even though the record is sort of, right now, the people living there and working there haven't seen an event in 7 years. Okay, and this is what that forecast looks like under uncertainty just for Montserrat. So So I'm thinking about here, right, so the probability that the eruption lasts T more years versus time. And now I've, to all of that data set, they'd fit in posteriors to these parameters in the distribution to reflect the epistemic uncertainty of this fit. So there's a pretty good spread on what that would look like. Okay, so prior to 2013, we sort of did a two-level model, a dynamic model of this system. And we saw that in these sort of high frequency periods, there were about 260 events a year. In the lower frequency, there were about 30 events a year. And even if you clump nothing in 7 years in there, that would bring you down to about 7 events per year in the low frequency case. And if you have a Poisson rate of 17 events a year and you see nothing in 7 years, that's probability 0, right? That's not going to happen. So what we were thinking about is, when we were thinking about this problem in the fall, is that we really need to think that something's switched to a low-level system. And this is reasonable in a few ways. In particular, we don't know that it's off, right? There's a probability that the system's off, but that's not clear. And there are events that sort of happen post-eruptive. Either there's one last sort of bit of sort of release coming from the system itself, causing an event. That event could be small or a series of small events. It could be one massive event. Also, there are, after things have cooled a bit, so it's maybe cool underneath, there can be structural deformation that leads to a massive flow event or a small flow event, right? So, and these can happen, 5 years, 30 years after. And so, what's that frequency? So this does happen at different volcanoes, but there's incredibly limited amount of data on this kind of behavior for these low frequency events. So we were quite concerned, what should we be using? One a year, one in 10 years, one in 100 years. But we sort of moved on without, worrying about that too much. And so then we said, okay, we want to sort of combine this low frequency idea with the duration, right? And in doing that, we come up with this posterior distribution, which you can write down in closed form for the duration. Right, so now we have our record of previous events. The last one is at Tn. We have these uncertain parameters in the duration, then we have this uncertain frequency. But here's what the posterior looks like. And so now if I want to sort of forecast that there's no PDC in the next S years, I need to sort of think about 3 different chunks of time. So, so the last event up to, say, the current time T, you can move current time around in this model, that's fine. And then I have a forecast window that's going to go S years past T. So this is a sort of second chunk of time. And then I can go past the forecast window. So here is what that posterior distribution looks like. And so basically 3 things could happen. It could be over already, right? Then we're not going to see a PDC. Like that event's going to happen if it's already over. So that's part of this contribution to the probability of no PDC. It could subside sometime during our forecast window. And if we see no PDC, that means, okay, before it subsided during that forecast window, we got lucky and no event occurred with this low frequency. Or it might not be over until after our forecast, but up to our forecast time, we again got lucky that no PDC happened at this low frequency. Right, so these are sort of the 3 components that would go into this forecast. And you can think about what this would look like now for different lambdas, right, for different rates. So here, here we have 1 per year. Basically, that model says, well, this would be over already, right? We're sitting in this, the eruption's already paused, so the probability of a PDC is 0, right? So this dark black curve is 1 minus the sum of the rest. You have a question? No. So now we play the same game with lambdas 1 in 10 years. So now you can see the sort of contributions from the 3. So this is a contribution that it's already over. And then we have And then we have that is going to pause during the forecast window, and that's going to pause after the forecast window, right? And again, the sum of those comes up to this probability of no PDC, and we have 1 minus that in dark. Play the same game for 1 in 100 years, right? We see something similar. Now, we were so happy about this plot when we made it. So here we fixed our sort of current time, and we fixed our forecast window. But you could do this for different forecast lengths and different current times. And looked at this probability as a function of that rate. And the really nice thing that happens is we have a very flat maximum that's somewhere near a tenth, right? So 1 in 10 years. And as long as even if you change S a lot, if you take it to 20 years, this thing will move down and over a bit. But as long as you're choosing this rate to be the sort of most conservative worst case scenario, the one that's going to give you the highest probability, we don't need to worry about quantifying that with data since there's basically no data, right? We're always going to be able to give a conservative estimate because of this behavior. Okay, so now we can think about sampling the sort of epistemic uncertainty in these forecasts. So this is, again, a sort of 5-year forecast. If we run this calculation with all of these alphas and betas that came from the posterior, from the duration work, and we see a spread of these posterior probabilities to reflect our uncertainty in the duration. This is the same picture turned on its side with kernels fit to it over time. Right, and we're just looking at the mean in pink and the mode in white there. Right, so basically for long times this is saying we're going to have something like a 15% chance of a PDC happening. Okay, so that's what sort of we're thinking about modeling. Is it over? And then is it safe? So here's the volume frequency record for flows at Montserrat. This is also, so we have an annualized frequency, and then we have volume in a log scale. We again get this linear relationship, which suggests this Pareto distribution. And this is also uncertain. There's a fair bit of uncertainty, because we only really have maybe 10 or a dozen events that are really informing that tail. So there's a fair bit of uncertainty in the slopes of that Pareto distribution. Okay, and so thinking about rare events, right, the Pareto model here is much more likely to observe far larger in scale events than those we've seen in recent history. So we're going to think about a record of 10 events, 10 volumes, and ask the question, what's the probability of an event that's 10 times bigger than we've seen in the record? And think about that for a non-heavy tail distribution like an exponential, and that's a pretty low probability, so about 1 in 200,000. If I think about this for a heavy-tailed event, that's going to be like more like 1 in 100, right? So, and this is a sort of thing that that because the data suggests that you're living in this case, you'd be you know, I would say negligent to not be exploring things that are a little bit bigger or a fair bit bigger in scale than have happened previously. If you were actually in this case, maybe that's fine. Okay, so we want to think about what's happening down there, and for that we have sort of physical models of these PDCs. So here we just have samples from a physical model. These models take somewhere between 20 minutes and an hour to run on a supercomputer. So not ridiculously long, but too long still, right? Too long to use efficiently. And so we see that these are really constrained by they're quite constrained by the topography, right? So these come from partial differential equations solved over these digital elevation models. And really what you'd like to be able to do is to explore both what happens at different volumes, and you can see the river valley it happens to head down is quite important. So here now I'm interested in not the probability that PDC is going to happen, but that I'm going to inundate some specific location with the PDC, right? So here's the expectation, the number of flows that indicate some specific location indexed with K, and we just have an indicator function that we've exceeded some critical height against this probability distribution describing the volumes in the river valleys, or the angles. And this is just if we're thinking about a Poisson model for the rate. And so the probability at one location is inundated over S years. Basically, this expectation gets stuck in here in the exponential. Right, so not just that an event happens, but that this specific event happens, that location K gets inundated. So Monte Carlo is expensive and doesn't really let us explore uncertainties, right, in this case, because each time I might want to evaluate this, it's going to be 20 minutes or an hour. Okay, so the idea we had a long time ago was that a given volume angle pair was either going to result in inundation or not if I run the simulation. And so for a while, we're going to sort of just divorce how likely scenarios are from understanding the relationship of will this location get inundated for which scenarios. So that's the idea, and then we're going to emulate the height of different scenarios, so here volume and angle, by treating it as a Gaussian stochastic process based on some training set, right? So this is so I have basically maybe 1,000 or a couple thousand of these physical simulations. For each location, I'm building an emulator so that I can sample for any scenario I like what would happen approximately for some volume and angle. Okay, and I think so that was our idea to sort of get over this computational burden, but I think we actually stumbled onto something that's more powerful, is that you really, if you want to explore aleatoric uncertainties and epistemic uncertainties, you shouldn't be pinning yourself to one distribution, right? So here I have some distribution of physical scenarios. I have my Monte Carlo samples. These happen to be scenarios that lead to catastrophe. So there were 30 of these. There's 4 out of 30 that are going to be hazardous. But then, you know, Stephen or someone comes along and says, well, you're really a terrible modeler. You should have been using this model. And this model now has 7 out of 30 that lead to hazard. And the key is, so you can do clever things with reweighting, but you cannot do clever things with reweighting if you haven't sampled near this threshold originally. Then you have to redo the process. And so I want to talk about that a little bit. Right, so Monte Carlo is slow, it's inefficient. So you might think, well, we could do some kind of importance sampling. And so here's just a you know, sort of cartoon example of 100-step random walks. I flip a coin 100 times. I want to know the probability of, right, so head step to the right, tail step to the left. I want to know the probability of ending at least 70 steps to the right. And that's really, it's binomial, it's really small. But can you simulate this thing? And the idea, right, so well, you can simulate it and it's never going to happen, right, for the rest of your life, running on all the computers you can get access to. Or maybe it would happen once. I suppose that's possible, but then you would have terrible statistics on it, right, because you keep running it and you'd only ever see that once. And so the trick here is to use a weighted coin instead of a fair coin that say, okay, I'm going to take 85 steps to the right on average and 15 to the left on average to end up near 70, right? And if you know how to do the weighting, you get a super efficient sampler and pin down this thing quite nicely. If you do the weighting wrong, right, so now if I weighted that I'm going to take 95 steps to the right and 5 to the left, you're going to get a terrible estimate because you sort of didn't capture this knowledge of where that threshold is, right? And so there's a big danger in sort of doing and uninformed importance sampling, even if you're seeing the events happen. And I think on a map, so if we're thinking about the probability of a hazard, the trouble too is that some location that's quite down valley is going to have a very different threshold than a location that's up valley. And so if I have a sampling scheme that's targeting one of those locations, it's going to inherently be bad for another, right? So you should use sort of smart sampling schemes, but you can't, there's not going to be something global that would work in a problem like this. Okay, so here's the results of an emulator at one site. So thinking about sort of the valleys, it's going down from 0 to 360, and then volumes of the events. So where I have black dots is where we've run these physical simulations, and then we have sort of a low threshold set that I've sliced there in red that says, okay, if I'm sort of above that, this location was inundated. If I'm below that, it wasn't. And this is just sort of the overview of that. And now my integral of saying, was I inundated or not, is really, am I on, what side of the curve am I on here? And this is looking at the mean of this Gaussian process, but by introducing Gaussian processes, you're also adding a bit more uncertainty for not actually running the model. So you could imagine having sort of samples of these curves and thinking about those in your integral. So now this is what, in the sort of simple case, the probability of our hazard becomes. So now we have this curve sort of evaluated in the indicator function for the Pareto density. And I think, and this one was uniform distributed for the angle. But the key is it sort of doesn't matter what aleatoric model I used here. This isn't going to change, right? This sort of separation from was this a hazardous event or not isn't going to change regardless of how likely that hazardous event was. Okay, so this is just a bit of an aside on emulating with zeros. Let me go back here. So I actually have a bunch more zeros that would be over here, and we've sort of, for this problem, came up with a judicious scheme to just include some of them. But if I had a lot of zeros, so this is just a sort of cartoon function, if I had a lot of zeros, well, this does not look like a stationary Gaussian process. Right, so and this is a problem that's been plaguing us for a long time. Trying to apply this to storm surge, this is a problem that's plaguing us particularly for the inland regions, which are really what you're interested in, because there are plenty of scenarios that aren't going to get those wet, or aren't going to get those more than a meter wet. And so the idea we've been playing around with is fitting a Gaussian process to the positive output data, and then imputing values at the zero output locations, conditioned on being a process that goes through these points. Right, so there we end up with these sort of purple points that are imputed, and we're treating them now as a truncated normal. So when I sample, so now I'm going to sample from the sort of purple and positive black together, and when I sample that, I'm just going to take the maximum of 0 and that the Gaussian process, and so then I'll end up sort of naturally transitioning this stationary process to zeros where it should be. So this seems to work pretty well. There's some issues with sampling these imputed sort of negative values. The Gibbs sampler works well for that. The other issue I've seen is, and this didn't happen on this cartoon problem because it had a relatively strong linear trend, but if you have a constant mean that's quite high for the positive parts, right? I'm not quite sure what to do with that to be sampling the negative ones, because you're never going to see those come from that process. They're going to want to just revert to that high constant mean. So this is still something I'm sort of thinking through. But back to our forecasting problem. So now I want to know the probability that a flow would inundate some location indexed by k after S years. So we had that same integral before that reflects that the volcano could be turned off, right? So here it's already off before current time. Here, these are the same ideas. You got lucky, an event didn't happen in the forecast window, but now an event is one that's inundating this particular location, right? So these bits are new, right? So we're not just interested in an event, but an event that inundates this particular location. And then the same thing when you're sort of thinking past the, it's going to end past the forecast window, but up to the forecast window I got lucky and this didn't happen. Right, so this is what our calculation looks like. And these are now what hazard maps look like if we're doing this at all locations. And we can think about now, sort of exploring different aleatory scenarios for the angle it goes down. So if we just think about uniform, which is relatively close to what the data looks like if you take the data collectively. You see our sort of 1-year map, 5-year map, and 20-year map. I don't know how well you can see this. So these are 1 in 100 contours around orange and 1 in 1,000 sort of around the yellow bits, and sort of how those expand in time. There are 2 other sort of interesting aleatoric scenarios for this. Most of the flows have gone to the east. So if you just put a point mass at the east, this is what we'd expect it to look like in 1, 5, and 20 years. The current dome is sort of sitting to the northwest. And so if there's some structural instability, there's a good chance it would go to the northwest. So you can explore this again 1, 5, and 20 years. And I think, sort of my, being charged with talking to the scientific advisory committee there about microzonation, I think the emphasis on this is really that there's not one map, right? That really this is a tool to explore what might happen given as sort of much data and as much physics as we can summon together. But often for geologists and volcanologists, maps are truth, right? So this is, how to communicate this idea that none of these represent some kind of truth, I think is my challenge. Okay, so I'm going to talk a little bit about epistemic uncertainty. So here I'm focused on the former capital was around here. And so now we're just looking at that location. And I have uncertainties in the duration model, and I have uncertainties in the volume model. And now I'm going to sample those in my probability calculations. So not just integrating over the aleatoric probability, but then repeating that integral for lots of samples of these parameters that represent epistemic uncertainty. And so I end up, and these are the sort of same pictures we were looking at before. I'm just taking here a histogram of these, again reflecting uncertainties up here for 5 years. And so here we see this histogram of probabilities. You also sort of see this sort of long tail sneaking up, right? And this is at 5 years, so we're about there. But if you go out, and again I have now these sort of stacked together in time, if you go out for 20 years, we get this interesting behavior that the mode of this posterior distribution reflecting the epistemic uncertainties is very different than the mean. In these maps, I'm reporting the mean, but maybe, so it's hard to know. It's hard to know what the right thing to report is, and would that be useful to the scientific advisory committee, or too much information? These are I don't know, right? This is something that needs some thought. But you can now sort of marginalize this calculation by thinking about what's just the contribution from the eruption duration being uncertain, and what's the contribution from the volume being uncertain. So marginalizing it over the other one, basically. And this is what we see. So if we marginalize over the volume and just look at the uncertainty and the eruption duration, we see this sort of curve like we did before with the eruption duration when we weren't thinking about a specific location being inundated. If you marginalize over the volume, you can see that this is sort of driving this behavior. In that some sense, this very skewness is being driven by the volume, and these high volume events these high probability events are likely being driven by the volume. But I do think it's a bit problematic in how to report this, since these are about an order of magnitude different. So that's where I'm at, and I think there's a lot of open ideas and questions. So how to communicate uncertain forecasts to various levels of stakeholders, right? So So scientific advisory committees, civil protection authorities, and the communities themselves, right? And I suspect those conversations should look different and should be coordinated. So a project I'm working on currently, or writing a grant for currently, is how to use these kinds of forecasts in ongoing crises. So volcanic crises are often a bit different than other sorts of natural hazards, because there might be communities living with a volcano. And even if the event doesn't seem that bad, sort of persistent small tephra fallouts on communities are super disruptive. So how can you sort of have forecasts that someone can use real time and adjust dynamically? So with our sort of setup here, we should be able to adjust these dynamically. Like, we can always put in different distributions to describe, sort of current behavior, at least as best we can. But how should that information be communicated, and how to make decisions based on that? I think this is also particularly interesting. I mean, it's perhaps more of a social science problem, but people react very differently if they've lived through a hazard or not, right? So how to be communicating that to the community is an interesting question. And then, and these might kind of all look the same, and I guess they're kind of the same, but there's this idea of sort of coupled hazards and multi-hazards and different kinds of hazard threats that might impact the same location, right? So, for multi-hazards, I'm thinking about, so Mount Pinatubo had a big tephra fallout, but it also was combined with a giant rainstorm, right? Which ended up being much more weight on structures than it would have been if it was just a tephra fallout. And that was just sort of happenstance that they happened together. For coupled hazards, I think there's multiple open problems. So the lahars I mentioned are sort of automatically a coupled hazard. You have to have a PDC deposit for that to happen. But something I'm really interested in is forest fires leading into landslides or mudslides, because those you very much. I guess it's sort of the same idea, but you can imagine sort of coupled maps there that would inform the hazards, actually probably for both. And then combining hazard threats, so particularly for volcanoes, you might be impacted by all three of these. So you can imagine by lahars and PDCs and tephra fallout. So you can imagine a sort of event tree scenario where you sort of stick all this modeling into the mapping of what's impacted, but then think about combining the probabilities for these different this. So I think there's lots to do in this sort of field, and lots of opportunity to sort of share this sort of data and modeling exercises with uncertainty with people that it might be useful for. So that's it. Yep.
Any question?
Yep.
So you said that they're thinking about mining, and they want to know the answers to these questions because they're going to mine. Would that change the landscape in any way that would mean that the simulations and the probabilities and the angles and all of those would change?
Probably not, but you raise a more interesting question. So the mining isn't going to be done on the flanks, and it's really the flanks that are going to drive the directionality. So if something is done down on the surface, it's probably not going to change the flows much. But what can happen, and what people see, both in reality and in simulations, is that you could have several events that fill in valleys. So you could have a sequence of events that fills in a valley, and now instead of being channelized by the valley, it's running over the valley. And so that I don't know how to deal with, right? So this is sort of, will one thing happen, right? And ultimately, it would be nice to be able to sort of have live updates of digital elevation models and just be churning this process in the background, but that doesn't seem realistic anytime soon. But yeah, that's something that we can't really deal
That's
with.
almost like in the model, though, isn't it? That whether that thing can happen.
It would be nice if it was in the model. It's not, yeah. So you could, I mean, you would have to have, there's not actually in this model we're working with, and it's quite common, there's not a deposition model. So this is sort of a live flow model for what would get hit. And the deposition is quite complicated because you could have an area that experiences a giant flow, you know, maybe 20, 30 meters high, and afterwards it's scraped clean. Right, so where the deposition happens is it's sort of its own process, and that's not something we're doing. So if you had a deposition model, then you can imagine sort of stitching that onto your digital elevation map and thinking about the process that way. It'd be nice to be able to do that, but I don't think we're there.
I'm not sure whether I understood correctly, but the physics models model just what happens once you've had an eruption of a certain size and there's a
Right.
stuff going in the landscape. Is there any physics model of the underlying eruption itself?
Yeah, so there are, and this is something we've been trying to think about how to incorporate. So there's this, this is a strange, right, small world. So there's this guy, Barry Voigt, who's a very famous volcanologist, and he happens to be John Voigt's brother and Angelina Jolie's uncle. But anyway, so he has this model of failure and sort of time to failure with stresses building up. And so this model has been around for maybe 30 years. And it's really was fit to sort of more mechanical systems where they could measure the strain rates and such. But if you're imagining these domes build up, their strain rates are increasing, there's going to be some time of failure. There's a sort of physics model to do that. Recently, some colleagues have been working on trying to add some discrepancy to that model, because that model, if you fit it to their own data set and leave out the last couple of points, it's completely overfit and misses them. So I think there's some work on how would you combine something like that with which is really going to lead you to the timing of the next event. But if you had precursor information and you had sort of so often there's observatories that are just sort of watching the dome grow. So you can imagine sort of being able to have some interpretation of what those stresses are as the dome's growing and building that into this sort of precursor model. The big question there, and I think that's sort of the direction we're going in with some of this stuff, we're very interested in getting precursor data in as much as we can. The big question there, and what my volcanology friends sort of disagree on, is does that precursor model tell you just about the time to failure, or does it tell you about something about the scale of the event? And so people disagree on that, and so I'm eager to get my hands on a data set that could say that these things do seem independent, or we need to sort of be modeling what these aleatoric scenario models look like based on the precursor information as well.
There was in the 1980s and 90s, there was all these fashionable models about self-organized physicality applied to things like sand piles and avalanches and...
sorry, the models about what?
Self-organized physicality.
Oh, okay.
On the same physicality.
Yeah.
If you have this kind of system, you keep adding stuff that makes it more and more stressed, you end up with failures.
It's a very similar model, it sounds like.
Indeed, but I mean, they're taking a very kind of coarse-grained view of it. They weren't really thinking about that as a mechanistic model to look at things, but rather saying this leads to these parallel distributions, these geometry distributions, I guess, of events.
Right.
Yeah, but those models wouldn't help you to make predictions because they don't say anything about the correlations between different events. That is just an observation.
Right. Yeah.
Really just follow on from the previous question, but what then are your statistical assumptions about the relation between what happens in the past and what happens in the future? Normally when people do something like use extreme value theory, for example, or something like flood exceedances, and typical model says that exceedance is about any given threshold occurs a Poisson process. So they're assuming independence there of
So we're assuming
what happens
independence.
before and what happens after any point in time. Whereas presumably that is, and this is the earlier question, that is not really the case with volcanoes.
Well, so in the data set at Montserrat, there's enough data to do the check, and the data doesn't show evidence of independence, or it doesn't have strong evidence against independence, right? So for Montserrat, it's fine, or it's reasonable to assume independence, but I don't know that that is universal, and particularly what Stephen says, if there was some correlation there, this is something we should be modeling. So we built models that I didn't talk about it today really, but we've built models that there is dependence in some of the scenarios, right? So you can build that into the model. The question is, if you're incorporating this precursor data, do you need to do that or not? Right, and we just don't know yet.
In the context of extremes,
Mm-hmm.
it's extremely difficult to detect dependence. I think you need a huge amount of data. And the thing that bothers me is that you could make predictions assuming independence, but how likely certain extreme events were in the future. And in fact, if you allowed for this additional uncertainty, you could make those predictions with a lot less confidence.
I don't disagree with that. I mean, I think we had strong evidence for independence for this case. Not that you always would.
Yeah, it must need some very detailed understanding of the underlying physical processes, must it not?
So yes, and then that happens. So when we've really seen dependence, the dependence has and so they're definitely, it's not a stationary process, right? So what ends up happening is there's a big event, the dome collapse. The dome needs time to rebuild, right? So that can happen at different rates, but often you will see a period of quiescence after a large collapse. The other thing that happens, and so, I mean, when we've done short-term modeling, we incorporate stuff like that. But taking the whole 30-year data set together and thinking about forecasts, there's just not strong evidence of that kind of dependence. There is evidence, too, of dependence on the angle. So what happens is if there's a big event, often it will take a chunk out of the edifice, and so now small events will sort of be directionalized that way. When the dome builds up again and you have a really large event, as we modeled it as doing a sort of random walk centered from where it was and going and then picking a new direction. And so I think it's you know, that assumption, I mean, I don't disagree that you should be very careful with it, but I think it depends on both the sort of the time scale that you're thinking about the forecast over and the data you have to support it or not.
Presumably these modelling results are being used in some way to make decisions around exclusion or economic development. So they're making some implicit or explicit judgment around sort of damages avoided,
Right.
versus opportunity costs, opportunity benefits lost.
Mm-hmm.
Could you say something about actually how these results are being used in decision making? Because you don't mention that as one of your how-to.
Right. So I guess that's you know, in the communication, particularly with the Scientific Advisory Committee, they're going to be thinking about that question. How they're weighing it, I don't know. I've seen other people do analyses like these for critical infrastructure. So in particular, there's the Snake River Plain in Idaho is a volcanic field that a nuclear research lab was built on. Right. So there, you know, there are studies in particular about, you know, thinking about with Nuclear Regulatory Committee, what are the risks associated with it, and how quickly would we, how quickly should we think about getting rid of this thing or not, right? So certainly I don't feel like I'm there. Not that I shouldn't be there in part of those conversations, but in the work I'm doing, I'm not there yet. And so I'm certainly interested in hearing about how to make this more informative for people who want to make those decisions. But I'm not the one making those decisions yet. But I mean, hopefully this would be informative, and how to communicate it to people or work with those people I'm interested in learning about. A similar study was done for nuclear facilities for a plant that was going to be built in Azerbaijan and near a volcano. The study was done and said, this is unacceptable to build it here. So I mean, there are people sort of working with that. I think with the sort of critical facilities, there's much more interest in the very rare events and thinking about the sort of methodology, you could say, to make forecasts, where in sort of places that are in ongoing crises, it's really very new. These ideas are quite new.
I've got one there.
Yep.
Catch. Whether when you emulate, do you emulate the map or do you emulate each point?
So you emulate each point.
Okay.
Yep.
Have you thought of emulating the maps?
So yes and no. So we've done the maps both with emulating each point and with doing the parallel partial emulator, taking each point as output.
Right.
Whether you guys would say that was emulating the map or not, it's a different question, right? But we've not done something like PCA on it. Yeah.
It might be interesting to compare the two and see what the game is.
Mm-hmm.
What the computational game is doing that.
Yeah. Yes. So probably not on this problem, but I think on the storm surge problem, yes.
Yeah.
So
Because then you can get uncertainty on the map.
right. So I feel like this is a debate Danny and I have been having for a while. That the emulating the map, we're still just emulating the physical model, right? And there are lots of correlations in the physical model between grid sites or between map sites, right? So it's not that you're losing those. You're not losing those physical correlations are still there. You're just saying how I'm approximating that function. What we're doing is not correlated.
Yes.
But the correlation's still there from the physics.
Physics correlations to level. When you draw, you
Mm-hmm.
can't draw a map. You can only draw individual points.
Right.
And that's the thing.
Yes. No, and that I agree on. And and again, Danny and I may disagree on this, but if it's going into a probability calculation and you're sampling a bunch of those, the correlations, again, not from the physical sites being next to each other, but just from approximating them, are going to get washed out in the integrals.
Yeah. I mean, I don't think one's right and one's wrong.
Yeah.
I'm not saying that, but I think it's an interesting debate we should have.
I do think too, though, one thing with so I'm more interested in perhaps doing this comparison for the storm surge problem, because either doing PCA on it or doing the parallel partial, the zeros are this big issue.
Yeah.
But you could imagine doing this imputed thing and then feeding that into either, right? And that would be interesting then to think about that comparison. So I think that might be the better problem to work on that on.
Any more questions for Elaine? Okay, thanks.